One of the most basic human abilities we have is the ability to order objects. And this is a very innate human instinct, which helps us just make sense of the world. And in mathematics, order appears in several different ways, and it has a formal treatment. And one of the most fundamental structures of order theory is the concept of a partially ordered set. So here on the screen, you'll see just several examples of how partially ordered sets can be illustrated. So for instance, here is the partially ordered set associated to the divisibility relation on the divisors of 36. And there's also other examples. So for instance, here is the partially ordered set associated to the subsets of a 3-element set. So if you have 3 different elements here, it's x, y, z. You can form 8 different subsets from it, and this is how they all are included in each other, forms a nice cube. And there are other kinds of partial order relations, and this just gives you, here on this picture, just gives you another kind of example, which comes from logic. All right, so let's jump straight into a definition here of what a partially ordered set is. So here's the definition. A partially ordered set is nothing other than just simply a set together with a relation on it, and that's supposed to represent the order relation. And that relation is not just any relation. Of course, it has to have some properties, and these are the 3 properties. There is what's called reflexivity. So that's just requiring that every element is related to itself. Of course, every element should be less or equal to itself. Just as in the integers, every number is less or equal to itself. Then it should also be transitive, and this is just this property here. So if we have x is less than y and y is less than z, then x should be less than z. Of course, if x is smaller than y and y is smaller than z, then x should be smaller than z. And then there is this property of anti-symmetry. So this is just saying that if x, this represents something quite familiar actually. So for instance, if you're thinking of x and y as integers, then this just says that if x is less than y and y is less than x, then they should be equal. So that is called anti-symmetry. All right, so let's jump into just a few examples here of how this works. So here is the usual natural number system, the counting numbers, 0, 1, 2, 3, up to infinity. And we want to equip this with the usual less or equal relation of integers. And let me just be very clear about what we mean by this less or equal relation, exactly what we mean. So if we're allowed to talk about addition of natural numbers, well, then we can define this less or equal relation in the following way. So for natural numbers, we can define x being less or equal to y, if and only if. So it's a statement here. This, of course, it's representing a statement. X is less than or equal to y according to our relation, if and only if x plus z equals y for some natural number. So we can write it in this way. So just to be clear about what's happening here, we are defining this statement in terms of a different statement, namely one which involves addition and one which just tells us that we are, the thing that we're adding is in the natural numbers. And now let's see that with this formal description, we can actually prove some things about the relation. So let's check reflexivity. So y, for instance, is it true that given any x, so if I give any x, why will it be true that x is less or equal to itself? Well, it's very simple. To verify this particular statement, what do we have to do? We have to deconstruct it in terms of its definition here, and make both of these statements true for a specific z. And we can do that quite easily, right? Because x plus 0 is equal to itself. And of course, 0 is a natural number. So that ends the discussion. So because this is true and this is true, we have that what we want is true. And you can use similar kind of arguments to verify the other properties. But anyways, this is just going to be verifying very obvious things, that the less equal relation is as you expect. But it does tell you that things can be a bit formal. Okay, let's look at a different example of a partially ordered set. And so in this case, we're going to be working with the natural numbers excluding 0. So the numbers 1, 2, 3, up to infinity. And we want to equip this together with the set, together with the divisibility relation. So let me be clear, what do we mean by this divisibility relation? So given natural numbers that are not 0, what do we mean when we write down that x divides y? Well, what we mean, again, this is a logical statement. This is a statement which is either true or it's false. And how do we determine when it is true or when it is false? Well, let's say again, we're allowed to talk about multiplication. Then we can actually make some progress here, and we can say that the way we define this relation is that x times z equals y for some z, which is a natural number that is not 0. So this is a statement, this x divides y, it's a statement, namely this one, together with this one. And just as we did for the lesser equal relation, we can verify that this is reflexive. You can do it almost very much the same way. And again, one can be very formal and establish that this relation has the 3 properties which make it a partially ordered set. It's reflexive, it's transitive, and it is anti-symmetric. But let's just compare this description of the divisibility relation with the lesser equal relation from earlier. So if we just go back here for a second, you'll see the way that we defined the lesser equal relation was in terms of addition, and that's just given here. And it looks very, very similar to how we define the divisibility relation. And in fact, the only thing that's different is just the operation. So the thing here, if I take just this one, the only thing that's different really is just the operation and then the set. I should have said the set. So if I replace the plus by multiplication and the set, I just remove 0, then I get the divisibility relation. And so what's quite amazing is that they have such a very close similarity, but they are really quite different. And let me just show you how these two relations are genuinely quite different. So here's our divisibility relation. And let me just show you one kind of difference between divisibility and then less equal. So for the lesser equal relation, if I give you, for lesser equal, if I give you any 2 natural numbers, then it is definitely true that either x is less or equal to y, or y is less or equal to x, of course. If I give you 2 numbers, one of them is going to be bigger than the other. It's as simple as that. And because we have such a close definition, just replacing multiplication or addition by multiplication, maybe the same thing is true for divisibility. But of course it's not. To show you that this is not, the corresponding statement will not be true for divisibility, well, we have to show that produce 2 integers, x and y, which are not 0, such that neither divide each other. And you can take, for instance, just 2 and 3, and you'll see that neither 2 divides 3 nor 3 divides 2. So these are not true. Okay, so let's move on to one more kind of example. Let's take a look at the subset inclusion relation. So given any set X of sets, then we can consider the relation of subset inclusion. So just to be clear, what is that? So given 2 sets, A and B, we write that A is a subset of B. And this is the symbol here for subset inclusion. And the question is, what does it mean? And the answer is, again, we can define it in terms of a logical statement. Now, I was writing if and only if earlier, but actually this is the symbol for if and only if. So you can think of it exactly the same as if and an if. And it's the logical assertion, the subset inclusion is the logical assertion that if I take any x, any set x, and I find that it's an element of A, then it should also be an element of B. And that's exactly what subset inclusion means. So again, it involves two statements, this one and that one, and they are connected in a different way. So for divisibility and less or equal, we had conjunction. We had that x divides y if something is true and something else is true. Here we have an implication, which is to say, if this one is true, then this one should be true. So this is just a different way of connecting logical statements. And anyways, we define the subset inclusion relation in this way. Now, equipping any set of sets X with the subset inclusion relation, which is just to say that we define the relation precisely as subset. So X here is a subset of Y. If that's what this means here. This will turn X together with this relation into a partially ordered set, and it is of course going to be reflexive. Let's see again. Y is a subset of B. Subset of A. Well, this is exactly the same statement as saying that if X is an element of A, then it should be true that X is an element of A. And of course, that's true. Any statement implies itself. If this statement is true, then of course the same statement is true. So because we have these identical statements here, the whole implication is valid. This whole implication here is a valid logical statement, and therefore this one is. So for that reason, this less equal relation up here, together with set X, is going to be reflexive. And again, formally one can check it is easily transitive, and it is easily antisymmetric, and so we have a partially ordered set. Okay, so let's go back to the first minute of this video, because I want to explain how we can arrive at these visualizations of partially ordered sets. So the first thing is that each of these pictures here represent partially ordered sets. So for instance, this one here represents all subsets of the three-element set, namely this one here, this three-element set consisting of just three symbols, x, y, z. And you can see that each of the elements here are subsets. So the entire partially ordered set consists of subsets of the three-element set x, y, z, and each of the green boxes here are subsets of that set. So in particular, here is the empty set, the set that contains exactly nothing. That is a set, and it's a subset of every set. And there is the entire set itself. And one thing to just keep in mind is that the set of all subsets of a set, it's called the power set. And in this case, the entire set is just the power set. It's got the power set of the set x, y, z. Okay, so it has 8 elements, and the question is, how did we arrive at this visual depiction of the partially ordered set? Okay, in order to describe to you how we can generate these pictures, we just need one very simple concept, and that is, what does it mean for an element B in our partially ordered set to cover another element A in the partially ordered set? So we say that B covers A if, firstly, A is less than B and A is not equal to B. And in particular, there is no element in P which is strictly in between A and B. So just to give you a simple example of where this fails, let's consider the natural number system here, together with the usual less than or equal relation as we defined it earlier. And let's give you an example where it fails. So let's take a particular case where A is equal to 1, let's say, and B is equal to 3. Then let's ask which one of these conditions fails. Well, firstly, of course, we're going to have A is less than or equal to B. So no problem there. And also, A is not equal to B. of course, 1 is not equal to 3. So both of these conditions are actually holding. So the only thing that could fail is that there's something in between them in our partially ordered set. And of course, that's true. If we have 1, that's less than, of course, 2, and that's less than 3. So the thing that's failing here is that there is an element which is strictly in between A and B in this case, and namely that's going to be this element 2. Okay, so now that we have this concept of what does it mean to cover, we can just quickly anticipate a general definition here, or a general algorithm. But in our picture here, the arrows represent that the given element of the partially ordered set covers the other. So there's nothing in between. If we look at the set of all subsets of this 3-element set X, Y, Z, there's no set in between here. And so that's what the arrows in this diagram represent. Okay, so now we're ready to formulate a general procedure for producing these kinds of pictures. And so here is that procedure. So the first thing to know is that these kinds of pictures actually have a name. They're called Hasse diagrams. And given a partially ordered set P, to produce a Hasse diagram for that partially ordered set, what we need to do is just follow these 3 steps. So the first thing is, for each element of our partially ordered set, this is going to be a node, so we need to assign that node a label. Then the second step, which is arguably the most important step, is that for each pair of elements, A, B, if B covers A, then we're going to draw an arrow from A to B in our diagram. Now we're free to manipulate the diagram, just as long as we don't change where arrows appear. But we want to arrange the diagram in such a way that arrows point in an upward direction. And this is the 3-step procedure for producing a Hasse diagram. And so let's put it into practice and see if we can produce some other kinds of Hasse diagrams. Okay, so let's produce the Hasse diagram of this very simple partially ordered set. So we're just dealing with a 3-element set 0, 1, 2, where the relation on the set is just the usual less or equal relation. So 0 less than 1 and 1 less than 2. Okay, so we have to assign a label to each element. And so what we're going to do is just put in, just use the same symbol that we did inside the set. So we have 0 and then 1 and then 2. Okay, so we've assigned our labels. And now what we want to do is put in the arrows. And we need to put in arrows where one element covers the other. So of course, 1 will cover 0 and 2 will cover 1. And so we have these 2 arrows. And we will have that 0 is less than 2, but 2 does not cover 0 because there is a 1 in the middle. So actually the Hasse diagram is very simple. It's just this diagram right here. Okay. So let's try a little bit more challenging of an example. Let's look at the divisibility relation applied to a specific set, namely this one. So we want to produce the Hasse diagram again, but now the less or equal has just a slightly different meaning. The less or equal here is going to be essentially just the divides relation. So we're considering the divides relation restricted to the set here. Okay, so at the very bottom, because 1 divides everything, I think that's where the 1 will go. So we put 1 here. Okay, next up, what covers 1? Well, what would it mean? If anything goes in between 1 and that number, that means it would divide that number. But since we're dealing with 3 prime numbers here, that could never happen. So we'll have 2, 3, and 5 here, and 1 divides all of them. So we have this and this. And there's no relation between them. There's no arrow here or that way or vice versa. So we don't put any arrows there. And we've now added in the 4 elements. Now what we need to add in is the last one. Okay, so the 30 goes above. And now we ask, well, does 2 divide? Well, it does, so we put an arrow there. 3 also divides, we put an arrow here. And then 5 also divides, and we put an arrow there. Okay, so this here is the Hasse diagram for this partially ordered set. And you can see that it looks a lot different to some of the others we saw earlier. And just to go back one last time, we can go to the first minutes of the video just to see these partially ordered sets one more time. So here it is. So this is the Hasse diagram of all the divisors. So if P in this case was equal to the divisors of 36 ordered by divisibility, then this is the Hasse diagram. Not the one in red. I'll circle the one now. It'll be this one here in blue. So if you take P to be the set of all numbers which are divisors of 36 and then order that by divisibility, then this is the partially ordered set you get. Okay, so I leave it to you to compute some more partially ordered sets and Hasse diagrams, but that's it for this video.